To fully understand the contrast of the SEM image, we must understand the principle of the formation of an SEM image. So, interaction of electrons with specimens. The scattering range of electrons inside the specimen is different depending upon the electron energy, the atomic number of the elements making up the specimen, and the density of the constituent atoms. As the energy is higher, the scattering range is larger. To the contrary, if the atomic number and density are large, the scattering range is smaller. Now, the Monte Carlo simulation enables us to understand these phenomena. Now, on the screen, there's a Monte Carlo simulation of electron scattering in resist on a silicon substrate at two different voltages. First, at 10 kilovolt, and the second one at 20 kilovolt. And this is obtained from the paper by Kaiser and Vishwanathan in 1975. So as we can see that the scattering is more predominant in the second image. Now, electron beam broadening, which is also called spreading in EM specimen, is a phenomenon that the electrons from the incident beam distribute wider than the beam size due to scattering by the atoms in the irradiated materials. So electron beam broadening affects especially the spatial resolution of the techniques on small electron beams. So beam broadening in a thick specimen is difficult to calculate because multiple scattering is involved. For example, it is greater than equal to 80 nanometers for silicon. The surface plasmon effects become negligible while the beam spreading becomes more significant because more electrons suffer inelastic collision in larger scattering angles and more electrons scatter outside the finite collection aperture. Now on the screen, we have beam broadening due to electron-electron repulsion, and on the x-axis, we vary the beam current in nanometers, and on the y-axis, we vary the beam broadening. And it has been plotted for 4 values: for 5 kilo electron volts, for 10 kilo electron volts, 15 kilo electron volts, and 50 kilo electron volts. So the beam broadening due to the electron-electron repulsion has been shown by assuming that 100 millimeter column length is present. So when beam current is high and beam energy is low, this has a major impact on resolution. To achieve high output in electron beam lithography also, a high beam current is used to reduce the exposure time. And electron beam current of greater than 1 microampere value is required to achieve 5 WPH for low density critical wafer layers. So the advantages of high beam energy above 10 kilo electron volt are that higher resolution is there with higher beam currents and less beam position drift is there due to external electromagnetic fields or changing fields. And advantages of low beam energy that is below 15 kilo electron volt is that less beam dose is there, which means we can resist sensitivity better, and therefore it allows a better output and also less thermal expansion. So to wrap up, basically, some researchers have theoretically studied beam broadening in thin films based on Monte Carlo techniques as well. And for a typical sample thickness of 100 nanometers, the beam broadening for rutile is about 8.5 nanometers at 200 kilo electron volt incident beam energy. So in principle, the beam broadening is weaker for thinner samples. This is the conclusion that I've arrived at. Thank you.